Yes. So you're starting today with try everything from Zootopia would be a great way to start the right mood for problem solving. So we have a special guest, Kayla. She is averaging less than 50% school over the past, I think, 8 days because of all the snow days.
Oh, it was Monday, Wednesday, Friday, and now I hope we have Tuesday.
Yeah, there's a good chance she'll be back on Wednesday. She won't be here on Friday because you guys don't have school on Friday. Okay? So what we're going to do today is we're going to start off with some munchkins. They need to be eaten. Kayla is definitely willing to do her job, but please feel free to help. We're going to do a little bit on... And she is not a munchkin, that's right. That's why I said eat the big munchkins, not the little munchkins. So we're going to do the arithmetic mean, geometric mean. We're going to do a little bit more on that. And then we're going to shift to various games. So we're going to do games later in the semester, but since Kayla is going to be here helping us today, I thought this would be a good day to do the games. Okay. Is it tracking? It's tracking now. Okay. So where were we last time? Last time we did the arithmetic mean, geometric mean. So AMGM. So we had numbers A1, AN strictly greater than 0. If one of them equals 0, this is really not much of a challenge. And the arithmetic mean was the sum divided by n. So this is the standard mean that you're used to. And this was greater than or equal to the nth root of their product. We gave a geometric proof when n equals 2. And we also gave an algebra proof when n equals 2. Now the question is, what is the correct base case? Should we be doing n equals 2 as the base case? What's the base case of the arithmetic mean, geometric mean? Do we start at 2, or is there another number we should start at? It may be easy. Yes?
I mean, 1 is very trivial, because it's always equal.
1 is very trivial. Yeah, we should still be very careful with that and make sure. I didn't even bother writing 1 because 1 is an identity. It's always an equality. The arithmetic mean and the geometric mean are the same. This is basically 2 different ways of averaging. And we talked about the Maclaurin inequalities, that there's a whole string of stuff in between them. These are extremely useful in a lot of problems. We really should have looked at n equals 1, not much of a need. Lots of different ways to prove it by induction. I'm going to do the hopping method. Okay, I think the hopping method is a little bit more fun. And so we also have Lagrange multipliers. Anybody have a preference to Lagrange multipliers first and then hopping, or hopping and Lagrange multipliers? All right, let's do Lagrange. So I've been doing a lot of shoveling. This will give me a little bit more time to recover. Okay? How many of you remember Lagrange multipliers from Calc 3? How many of you understand why Lagrange multipliers work? So you want to maximize or minimize f of x subject to g of x equals c. I'm just putting an arrow over x to just remind ourselves that x is probably going to be x1 through xn. And the condition is that it's necessary for the gradient of f at our special point x0 to be some multiple of the gradient of g at the point x0, with lambda some complex number. Typically, of course, actually, since we're doing this real values, lambda will be r. So what I wrote is right, but not really as good. So the question is, why is this true? So one of the big themes in the course is whenever you get something, always go to an easier case. So this is a multivariable calculus problem. What is the simpler problem to look at? Single variable. So let's go back to single variable. What does the derivative tell us? Okay, it tells us the slope. So what does that mean?
Rate of change.
Rate of change. So if f prime is greater than 0, f is increasing. If f prime is less than 0, f is decreasing. Now, we could have a strange function such as f of x is x cubed, and the plot of this function is going to look something like that. And so it has neither a max nor a minimum. So if you want to find extrema, a necessary condition is that the first derivative vanish. But it is not a sufficient condition. And the idea is if the first derivative is positive, well, if you just keep going to the right, things will be larger. If the first derivative is negative, if you go to the right, it'll be smaller. If the first derivative is positive, if you go backwards, then the function gets, the first derivative is positive, the function will get smaller. So if I'm looking in one dimension, are the only candidates for extrema places where the first derivative vanish? Are there any other candidates? Yes?
Maybe at the endpoints of the interval.
Thank you. I was actually about to run into the blackboard, which is what I do every year when nobody remembers. So please remember to email me, because I'm thankful not to have to run into it. There we go. Where am I traveling at my fastest speed? Like that. Okay?
Does that hurt?
A little bit, yes. What was your name again? Okay, okay. You look familiar. So, endpoints are important. It's very easy to forget them, and that's why I figured I'd still run into the board. Okay? What happens when you go to several dimensions? Well, let's look at what's going on. So imagine we have some surface g of x equals c. The gradient of g is the normal direction. Imagine the gradient of f is not completely in the direction of the normal. Then what we can do is we can write this as some component in this direction and some component perpendicular to that. So if the gradient of f is not aligned with the gradient of g, if it's not aligned with the normal, then if we move in this tangent direction, it increases. If we move backwards, it decreases. The proof of this is so nice and so geometric, it's worth just reminding you of this great result in Calc 3. And this is why we get the necessary condition that the gradient of f and the gradient of g must align. Okay, so this gives us the candidates to check. I love the method of Lagrange multiplies. It is huge in economics. It is a great way of attacking a variety of problems. So let's consider what we have. So for us, we have a1 plus an over n, and we have a1 an to the 1 over n. So we're trying to figure out which do we want to be our function and which do we want to be our constraint. Which would you rather have as the constraint? Or does it really matter? Yes?
I think I picked the first one.
Okay. So you want this as the constraint?
Yeah.
Okay?
It's a pretty easy gradient.
But here's the thing. Don't we have to take both gradients?
Yeah. But that way we can say that the minimum or maximum of the bottom one exists when its gradient is just this constant.
Okay. So we've got to be careful. In some sense, we have to take both derivatives no matter what. But we want to have a good constraint. Now, the a's are non-negative. If we assign this sum to have a fixed value, that's going to tell us the a's are bounded. If we assign this to have a fixed value, the a's are not bounded. Right? If I want this to equal 1, I could have a1 going up to a quadrillion, a2 going down to 1 over quadrillion. So this is actually better for the constraints. This leads, if this is constraints, we get a bounded region. So I actually do think it makes a difference to say that that is the constraint. Does it matter what value we assign for that sum? No. Because if I multiply everything by 5, I change this sum by 5, I change this by 5 to the n to the 1 over n cancels out. So I might as well assume the sum equals 1 or the sum equals n, whatever I want. So without loss of generality, what would you like this sum to be? What would be a good value? There's only one number we have to stay away from. 0. As long as it's not 0. Kayla, can you give me a value other than 0?
2 million.
Last time you get munchkins. Really? You don't want to do 1?
They're both not.
They're both not 0. You want to do 2 million?
Yeah.
Alright. So this equals C, and C equals 2 million. So much nicer when you're 3 or 4 years old. Why did that do? Okay, so we'll do 2 million. Okay? So this is our constraints. This is the function we want to maximize or minimize. Okay? Now there's a couple of ways we could do this. What function should we maximize? Yeah?
The second one, right?
Wait, do we want to maximize this directly?
Or we can maximize its reciprocal.
Not quite the reciprocal, close. Reciprocal would be 1 over. I think there might be something a little bit, I mean, it doesn't really make much of a difference, but what function might be easier to look at? I'm sorry?
Just the inside.
Yeah, just the inside. If we find the maximum value of the product, that's the same as finding the maximum value of the product to the 1 over n. Or same thing for the minimum. You might have seen this when you're trying to do calculus problems about minimum distances, and rather than looking at the distance which involves the square root, you would just square things. So maybe what we'll do is we'll take our function f of x to be a1, a2, dot, 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 an, and we'll take our constraint function g of x to be a1 plus an over n minus c. Okay? I think I am going to overrule my daughter, and I might choose c to be 1. Just because, as fun as it is to work with 2 million, we'll see if it matters. We'll try to keep c as free as long as possible. But the nice thing about having c equals 1, that could simplify something. We'll see. Maybe it doesn't matter. Okay, so let's try to apply the method of Lagrange multipliers now. So the first thing is we need to take the derivative of either f or g. Let's see. The gradient of f is going to be, well, let's look at it. So we first take the derivative with respect to the first variable. So remember, gradient of f is df dx1 df dxn. Except I guess in this case we're using a's as our variables. So when we take the derivative of this with respect to a1, we're going to get a2 times a3 times an. When we take the derivative with respect to a2, we'll get a1, a3. So what we really have is we get the function f again divided by a1 in the first component, divided by a2 in the second. And so after a little bit of algebra, we see this equals f of a, and then it'll be 1 over a1, 1 over a2, dot, 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 1 over an. Everybody comfortable with that? Because in the first one, I just lose the a1, so I multiply by a1 and divide by a1. I just multiply by 1 to make the algebra nice. For the gradient of g, well, it's just going to be 1 over n, 1 over n, 1 over n, 1 over n. So it's going to be 1 over n times the vector of all 1's. Right? So grad f being a multiple of grad g, well, this is really easy to solve. Since all these components are the same, what must be true about all these components? Same. Therefore, only one critical point candidate. A1 equals A2 equals AN. Have we found a maximum or minimum? How do you know it's a minimum?
You can test other points.
So you can test other points. So what we can say is, well, look, we know that if we look at the sum, if the sum equals C, if I increase A1 and decrease A2, I'm not going to change the sum, but I can really decrease this product. I can make A2 very close to 0, and I can make this product as small as I want. Right? If I just shift a little bit around. So we can see that we can make G very, very small, so the minimum value is going to be when they're all the same. And when they're all the same, then each one of these is just C over N. And then the rest is just algebra. So if they're the same, then we get G of C over N all the way to C over N is just going to be, we're trying to maximize F, I'm sorry. Okay. So now we take a product which would be C to the N over N to the N. Then we take the nth root of that, and we would just get C over N. Oh, sorry. Each one of them is equal to C times N. Sorry. Because we want G of X to equal 0. So we need each AI. No, yeah, I'm sorry, each AI is just C. Sorry. So it's going to be C, C, C. And so when we put that all equal to being C, we'll just get C to the N to the 1 over N, so we just get C. Which is exactly what our sum is. Yes?
Why was the gradient of F 1 over A1?
Well, because if you look at what F is, when I take the derivative with respect to A1, I get A2 times all the way to AN.
Yeah.
I multiply it back by A1 and I divide by A1. And I get F divided by A1.
And you say F is 1.
Well, I'm just saying, I can just pull it out. It doesn't matter what the value is. It's something that's non-zero. So because this is non-zero, the only way they can be equal is if the components are all identical.
Okay.
And so now we can just go through and say that the minimum value is occurring here. And this is going to lead to the arithmetic mean, geometric mean, when you do the rest of the algebra. Yes?
Why is it the minimum?
So we know it's either a maximum or a minimum. And if we take the limit as, say, A1 goes to 0, we can move A1's value over to A2. And this product is then going to go to 0. Oh, sorry.
I think it's a maximum.
Oh, wait, so we were doing it as a maximum.
Yeah. I think
Sorry. Okay, yes. It's a maximum, not a minimum. You said it wrong and you tricked me. Yes, sorry. It's a maximum because we can make this value smaller and smaller and smaller. So what you need to do is, this is the brushstrokes. Go through, do it carefully, put in the details. You can see sometimes it's a little bit annoying because now we have this is equal to 0. So we want to really compare this expression to that expression. Okay. I believe the following is a false story, but it's a funny story, so I will tell it. There is a story about when they were making the stealth bomber and the stealth fighter. What do you think they were trying to maximize? Stealth. They didn't check to see if they had a maximum or minimum, and they actually built the I'm here plane. Now, almost surely this is not the case. I doubt that the engineers are this absent-minded, but it is very easy to forget to check and see, do we have a max or do we have a minimum? Also, there's some deep real analysis results lurking in the background. Real analysis is not a prereq for this class. How many of you have done real? Okay, so the first question is, do we know that there actually is a maximum or minimum? Well, we have a continuous function on a bounded closed set, or a continuous function on a compact set. There must be a maximum or minimum. So that's the nice thing about looking at a bounded region. We know there must be a maximum or minimum. And then because this value G, this sum is constant, if we know that this value is at least as large as this, and this is the maximum value, then any other value of A's that have the same sum is going to decrease F. So we know at this critical point, this sum, which is equal to C, is equal to this product, which equals C. So at the critical point, they're the same. So at critical point, we know a1 plus an over n equals c equals a1 times an to the 1 over n. So at the critical point, they're equal. Since this is the maximum value of the product, any other value would be less than or equal to this. And since we were assuming that the sum is constant, we know that this has to be greater than that. So this is the final push of the arithmetic mean, geometric mean. Okay? So we know that we can restrict ourselves to places where the sum is constant. And because of that, since this is the maximum value, we win. Okay. Any questions on the Lagrange multiplier? It's a wonderful technique. You need to figure out what you want to be your constraint function. You need to figure out what's the right way to do the algebra. And so the nice thing here is we notice we can pull out the f of a, and that makes things very, very simple. And now we just have the reciprocals all have to be the same. Okay. Let's do the other proof, which is the hopping induction. So I like hopping induction. There's also a way to do it just by standard induction. The proof is not surprisingly standard, and I will leave that to you to look at in the notes. So the hopping proof. Show true for 2 to the m, then hop backwards. And actually this goes in line with the theme song from Zootopia, which we were playing earlier today. What is the name? This is not for Kayla. What is the name of the bunny in Zootopia? You have to give the students a chance first.
Hops.
Hops, right?
I know.
Wait.
Her first name?
What's her first name?
Judy.
Judy Hops, very good. Right?
And Hobbs is spelled with 2 P's.
And Hops is spelled with 2 P's. I did not know that actually. Thank you.
H-O-P-P-S.
H-O-P, excellent. So if you want in a moment, I'll have you do some hopping. Okay? So the question is it easy to do for 2 to the m? So, proof. We've already done the base case. Or we could always do m equals 0 for the base case, and that's not going to be a problem. That's pretty straightforward. That's essentially breathing. There's nothing to do when m equals 0. So now, in inductive step. Assume true. Now we could do for m and then show it's true for m plus 1, or we could do it for m minus 1 and show it's true for m. It doesn't really matter. We'll assume true for m. Show true for m plus 1. Okay? I'm going to let x, I'll use lowercase then. I'm going to let x be a1 plus a2 to the m. And I will let, I'm trying to think if I want to divide by, I'll let it a2 to the m plus 1 plus a2 to the m plus 1. So we'll see in a moment if I actually need to divide these by a value. Yeah, let's divide it by 2 to the m. We'll start off with these as the averages. What do we know right now? So what do we know? Hopefully we know something. Something more than just hops is spelled with 2 P's if it's from Zootopia. Yes?
The arithmetic mean was x plus y over 2.
Good, so we know x plus y over 2. What do we know about this? So,
Arithmetic mean.
I'm sorry?
It's the arithmetic mean.
What do we know about the arithmetic mean?
It's greater than or equal to the square root.
It's greater than or equal to the square root of xy if m is greater than or equal to 1. So sometimes when you do these proofs, you actually need to do a non-trivial base case. So if we want to do the induction, what I'm trying to do is I'm actually trying to use this twice. I'm going to use the inductive stuff. In some sense, this is very close to strong induction. Induction says you assume it holds for m, you show it holds for m plus 1. Strong induction is you assume it holds for everything up to m. And then, well, there's really no difference for regular statements between induction and strong induction. If you go into transfinite induction, sure, but we're not going to do that now. So we're assuming m is at least 1, and we can use the result from before, which is a non-trivial result. All right, so we now have this relation. Do we know anything about x? What do we know about x? So x is a1 plus a2 to the m over 2 to the m. Do we know anything about that?
It's greater than the geometric mean.
So it's greater than or equal to a1, a to the 2m, to the 1 over 2 to the m. That's by the inductive hypothesis. And similarly, we know y, which is a 2 to the m plus 1, plus a to the 2 to the m plus 1 over 2 to the m is greater than or equal to a 2 to the m plus 1, a 2 to the m plus 1. I hope people at home can see where the plus 1s are, to the 1 over 2 to the m. So we're really just using the inductive steps. We're using the inductive assumption in two different places. One on x and y, it was a clever grouping, and then one on what x and y are. So the reason I really want to go through this proof is it's a great technique. It's this idea of doubling. And it's this grouping of parentheses. And it leads to a lot of great efficiencies. So now we can combine everything. We've got three statements here. Let's just put them all together and see what we get. And so when you combine everything, you get x plus y over 2. Well, x plus y over 2 is just a1 plus a to the 2m. And then each was divided by 2 to the m. We divide by 2 again, and that's 2 to the m plus 1. You can begin to see now why I chose to do things this way. And now if we look at the product, x, y square root, well, we have a1 to a2m, taking out these. They were all to the 1 over 2m, but we take a square root, so we get another one. So we get a1, a2m plus 1 to the 1 over 2m plus 1. And we have the greater than or equal to from the m equals 2 case. And so this proves the inductive step. Yes?
For your numerator in the x plus y over 2, why did you stop at a?
Because I did not. Yes, because I did not do a good job writing it on the board.
Yeah.
Yes, thank you. And so we have all the terms here. It's defined to be the mean, and we broke up the mean in a really good way. Kelly, do you want to do some backwards hopping, or do you want me to do it?
What do you mean by backwards?
This math proof requires backwards hopping.
Backwards.
So you can be going like this. All right, so can you dumb it? Good job. Good job. You were in a munchkin for that. Okay? So the way this backwards hopping works, how many of you have ever seen backwards induction before? This kind of hopping induction. There's a class of numbers where it's easy to prove the result. You prove it for the result, and then you fall backwards. Did we talk about Strasson's algorithm for fast multiplication of matrices? Okay, there's ways to multiply matrices a lot faster than you would expect. There's ways to multiply numbers faster. There's ways to do Fourier transforms faster. It works best if your number is a power of 2. Not every number in the world is a power of 2. Kayla, can you give me a number that's not a power of 2?
3.
Thank you. 3 is not a power of 2. So what you do is you fill things up. And that allows you to use these results. So now, we're going to hop backwards. And then we'll shift to games. Okay? Assume n is not a power of 2. Okay, so choose the smallest m such that n is less than 2 to the m. So we have our numbers a1, a2, an. And I'm going to pad the sequence so that I have 2 to the m terms. And I'm going to pad it with the same value. So how many terms do I need here? I need 2 to the m minus n terms. Okay? Why do I want to pad it? Because now I have 2 to the m terms. I now have my result from before. I need a good choice of A. What do you think big A should depend on? So one possibility is A equals 1.
Yeah.
That's one possibility. What else could it depend on?
Maybe we can use the arithmetic mean.
Yeah. So the two possibilities is try A equals 1, try A equals A1 plus AN. Or maybe A1 plus AN over N. Yeah, the question is, which way do we want to do it? I think I want to do it this way. Let me just quickly take a look. Yes. So I want to try this, which is the arithmetic mean. But when you're thinking about the candidates, the most natural thing to try is 1. The second most natural thing to try is something related to A1 through AN. Maybe the arithmetic mean or the geometric mean. One of those two things would be a really good candidate to try. And again, I really want to go through the thought process of how you attack problems like this. All right, so now we can just apply the arithmetic geometric mean. And everything from this point onward is algebra. So this is why I don't have to prepare this lecture that well. I just have to know what I want to try, and then I just have to try to avoid doing algebraic mistakes in public, which, as you saw from over here, happens, but fortunately you guys are alert for 9 a.m. Okay? So let's see how we would do it. So we know the arithmetic mean is greater than or equal to the geometric mean. So what's the arithmetic mean? It's going to be A1 plus AN, and then we have the same common value every single time. So that's going to be 2 to the m minus n, a over n. And we divide that by, what do we divide that by? We'll divide that by 2 to the m. Right? That's the arithmetic mean. And that's going to be greater than or equal to the geometric mean, which is going to be a1, a2, an times a. And how many times do we have a? 2 to the m minus n. And we raise this to 1 over 2 to the m. Yes?
When we took A over N instead of AA,
Sorry, you're right. This is just a, not a over n. Thank you. See, I told you there'd be algebraic mistakes. Now, what would be a really good value to take for big A? Well, I mean, do we have freedom to choose a value for big A? I mean, without loss of generality, we can always assume that the arithmetic mean is any non-zero number. If we wanted to, we could choose big A to be 1. Doesn't really matter, but if we had wanted to do that simplification, we could have done that. If you look at what's going on here, this thing over here is A times n. So this sum over here cancels the negative and a. Then we'll have 2 to the m over 2 to the m. So we'll be left with just a, which is the arithmetic mean. And that's going to be greater than or equal to a1 an to the 1 over 2 to the m. And now what do we have over here? We'll have a to the first power, and then we'll have a to the negative n over 2 to the m. Well, the a's cancel, right? We bring this a to the negative n over 2 to the m to the other side, and then we would raise both sides to the 2 to the m over n. So you would get, bring over raised to the power of 2 to the m over n. And when I do that, when I take this to the 2 to the m over n, this is going to become the nth root of that. And when I bring this over, and I take that to the 2 to the m over n, I'm just going to get a. And so this will then give us a, which is the arithmetic mean, is greater than or equal to the geometric mean. I actually like not choosing a to be 1 here, so you see what's going on and you see how things are combining. If you choose a to be 1, I think you lose a little bit. I like to keep units when possible sometimes. All right, so this is more than enough proofs of the arithmetic mean, geometric mean. There are additional proofs. At least one more is in the handout. It's that important. Okay. Which one do you want to do? Do you want to do triangle? Do you want to do flags?
Flag.
All right, we're going to do flags. All right, we're going to shift to games.
Yay.
Okay. So, not surprisingly, all of these games have a great math component to it. My daughter and I are going to play a game called Flags.
Flag friendly.
How many of you have ever played Flags or played a close variant called Spot It? Okay.
Spot It.
Did you know Spot It?
Yeah.
Okay.
This is spotted. It's like spotted with flags.
So first, here are the countries of the world that matter according to the game. If your country is not here, I do apologize. Okay. Are they mixed? So they're mixed. So the way the game works is the following. First, I stack the deck.
Alright,
So, I know. No, I just want to show them what a card looks like. So here's a typical card, and I'll just move this closer so the people at home can see. What can you tell me about the card, Kayla?
it has different flags from around the world.
How many flags?
8.
8.
And they're from different continents. Some are from North America, some can be from South America, some can be from Africa, Europe, Russia, Australia, and
Russia's not a continent. Almost, but
Asia.
Asia.
And they happen to have one for New Zealand.
Right. I think they put Asia and Australia together. And so each card has 8 flags. And what happens is we each start off with a card. And whoever sees a match first wins.
But gets the card.
Gets the card.
But if you come upon a map, this happens to be a map of Africa.
Right.
So
We're gonna
if there's one
right.
on
We're
there,
gonna skip that in the interest of time. We're gonna skip things like that. All right. So Kayla, you choose your card. All right. I'll choose my card. Or does anybody want to play against Kayla? I can beat her in this. I mean, other things.
yeah, we have to put that in.
Okay. All right. I'll choose my card.
Ready?
And we're gonna. So I'll let everybody see my card. So the flip.
Got it.
We're gonna have to do this. Okay. Use this as a. All right. So we've turned over a card.
Alright.
And so this is really not fair for the people at home. So do you see? I see your match. Oh, I should have a generic card, not a continent card. All right. So I have a generic card, and Kayla and I are trying to find a match. Do you see your match? I see your
yes.
match. Okay. What's your match?
India.
All right. So so we're gonna move our cards over so everyone can see it from up here. So this was the card that we were trying to match. Okay. Kayla has India, which is on this card. My card has. Let's see, what match do I have? I have South Africa, thank you, which is where my advisor is from. Okay? So here's something that's interesting. Kayla and I each had a card, and a card was turned over. The game, what would make the game really unfair? Wait, I'm sorry? Yeah, if someone didn't have a match. So no matter what card is turned over.
You always have a match. No matter what card you
And how many matches do you have?
1.
You have one and only one match between your card and the card that's turned over.
Well, unless
So we're
if
skipping the
you're playing
continents.
with the continent,
We're skipping the
and
continents.
you have a continent and it's flipped over the same continent, you have every single flag on it.
And if you flip over a different continent, you have no matches.
And the other person can just take their time to get it.
Exactly. You can kind of go back and say,
And
have a
then
munchkin.
so if you have like Asia, the other person that's North America, and Africa and Australia. Well, Africa is split.
Right.
You can't.
Right. And the game. So we're gonna assume that there's no continent cards. This is amazing. The game is structured so that on every turn it's completely fair. We both have the same chance, 100% of having a match. No one has more matches than another. We both have exactly one match. So here's my question to you. There's got to be math behind this. How does this work? What math makes this game work? So this is the application of a basic counting thing in mathematics. It's become a card game that people use to make money.
Dad, we could start.
All right. So we're gonna shift to the triangle game.
So I win?
The triangle game.
Yeah, I win.
Okay, you win this one. All right.
Okay, well, put the.
Do you have the money?
Oh yes,
Okay.
I'll get it.
Okay, if you beat Kayla, I will give you $20. She has played this game with me so many times, the triangle game. I am confident on her chance of beating me. Anybody want to go against Kayla? All right.
You. Every one move I do.
So there's two ways to do it.
You can.
So to get $20,
You.
you and Kayla alternate moves.
But.
Or to win $1, you can get 4 moves in a row to every move she gets. Which do you want to go for?
I'll go $20.
$20. Okay.
Alright, this is the $20.
Okay, yeah.
Canadian.
Yeah, well, I'm not crazy. Yeah, I'm going to protect myself a little bit. I'll use 20 Canadian. All right. Here's how the game works.
Ooh.
You take a triangle.
Can you make that memory? Just down there.
So what I'm going to do is I'm
All
going.
of those are triangles.
Well, they will hopefully eventually become triangles. Guess this one's going to come.
Hopefully, and we can say this.
Well, the thing is, I can draw extra things, and as long as everything is a triangle, it's okay at the end. Okay.
Oh, I got this.
That's not a triangle. Okay.
Alright,
So.
wait, I want to write this.
You right.
Bottom right corner.
Bottom right corner. Thank you. Okay.
The one above.
And one above it.
Yeah.
Is there anything? And this one. Okay. But I mean, I want something that doesn't look too. Okay, Caleb, what number goes here? 0. What number goes there?
1.
And so this is the 0, 2 side.
This is it 1, 2.
And what's the bottom?
That is a 0, 1. So on here, so anywhere between this 0 and 1 on the bottom part, you have to put a 0 or 1. Anywhere between this 0 and the 2 on the outside, you have to put a 0 or 2. And anywhere between this one and the 2 on the outside, like here and here, you have to put a 1 or a 2.
So you understand?
Yeah.
So
Do you want to start? Or?
So Kayla, since she has the home field advantage, she's trying to get a triangle labeled 0, 1, 2.
Yeah.
Your job is to make sure she does not get a triangle labeled 0, 1, 2.
Okay.
Do you want to have alternate turns, or do you want to have 4 turns for every turn she gets?
I gotta go for the one turn every turn she gets.
Alright.
Wait,
Big
so
bucks.
so.
Do you want me to go first? Okay.
You can go
Wait,
first.
Daddy, how does he win?
He wins if he can prevent you from getting a 0, 1, 2 triangle.
I don't. I'll play my hardest.
So
I'm
you
gonna go my
so you choose where you want to go.
Oh,
No,
you
you
put
put
it-
it at a vertex.
At a vertex. Oh.
So
So then,
here
okay.
you want a 0.
Okay. I'll put it at this vertex then.
So he put a 0 there. So she could win immediately by going over here and putting a 2. So you know what we're gonna do? Yeah, Kayla. We're gonna let him have a couple of turns. You keep putting in some 0, 1, 2s, and I'm gonna give you an up. I know you like ups. So you just go.
Okay.
Take a couple of turns. Take a couple of turns. Now, based on the fact that I'm willing to give my daughter quite a lot of ups, and I put $20 on the board, what do you think his chances of beating my daughter are? How low?
Less than 5%.
How much less than 5%? I'll give her some bouncy as possible.
Close to the point where she's guaranteed to win actually.
Yes. In fact, she doesn't have to do anything. Eat another munchkin. That's how confident I am she's going to win.
Wait, so how many places should I?
You can keep going.
I can keep going.
You can't win.
Can I really not win?
You really can't win. No matter what you try, she will win.
2.
So over here, you've
Is it
got.
already defined as 1 on the corner?
Yeah, but she'll
Okay.
just put a 2. So she would want to put a 2 here. So to
Oh.
stop her, you have to put either a 0 or 1. Let's say you put a 1.
Yeah.
Then you can be fine over here. I don't want to put a 2 here, so maybe I'll put a 1 here. I'll put a 1 here, 0 here, 1, 1, 0. Now, but over here, I've got to have a 2. And then I can start looking at what happens when I fall down. So I'll leave this for you guys to think about. And you can just try it on a piece
I
of
could
paper.
do 2, 0, 1.
No matter what you try, there will always be a 0, 1, 2 triangle. It turns out that this is related to a proof of the Brouwer fixed point theorem, which is one of the most, it's not even worth picking up, it's 20 Canadian but high. This is related to a proof of the Brouwer fixed point theorem. This is one of the most important theorems in all of mathematics. I actually keep Canadian money on me because we are so close to the border. If I ever have to run quickly. Now, is going to do the rectangle game next?
Oh,
Yes.
yeah.
Okay. So I want you to.
Pieces?
No, well, they're smart enough that they can do without the toy. So I want you to try to think about why this works. Now the other thing is, what is an easier version of the game to play first? So one is a smaller triangle, but what else could you do? This is a big theme for the class. Think of easier problems. What would be an easier problem than playing the triangle game? Yeah, the line game. Okay, so the line game, it's really clear.
Yeah.
Here's a 0, here's a 1.
Oh,
The line
yeah,
game, you're
yeah.
screwed. Right? So, however many chops I have, I've got to go all zeros from here. I've got to go all ones from here. There's going to be a problem. So whenever you see something, your first thought should be... Exactly. Your first thought should always be, what's a simpler case I can explore, and can I get something from this? What you should do is you should play the line game several times, and then look at how many times there's a 0, 1 segment. Don't say, okay? Just look at how many times there's a 0, 1 segment, and that could be something, an interesting result. Okay? We have time for one more game. Yep, it's more than just that. All right, so does everyone understand the purpose of this game? There's a lot of really good mathematics behind this, and the proof is actually an extremely powerful problem-solving principle. No, we're going to do the rectangle game. So the last one is you have a 1 by 1 square, a 2 by 2 square, a 3 by 3 square, an n by n square, and so on and so on and so
Well,
on.
you have up to a 15.
Well, when I actually print out the toys, I actually have the physical toys. I did up to 13 by 13, but it gets expensive beyond that point, so I stopped at 13 by 13. And when I go to the elementary school, I actually bring this so that the kids either individually or in groups of 2. And so my daughter, what's your favorite shape?
Zeta.
No, try again.
When I was young, it was a rectangle.
Rectangle. So when she was young, she loved rectangles.
Rectangle.
And so when we put these squares down, we're going to put these squares down one at a time. Rectangle. We're going to put these squares down one at a time so that we always have a rectangle. You can't put a square on top of a square, and they have to be aligned. If you can put down 2 squares, I'll give you 20 Canadian.
No, if you can put down 2 squares and then make a rectangle.
And still make a rectangle. It's got to be a rectangle. Is it possible to put down 2 squares? No, because whatever square you put down, if you put down the 3 by 3, you'd have to have another 3 by 3. This is yet another example of a rigged game. There's a huge advantage being a math professor when you're playing games against your kids.
This is what you did last.
Alright, so to make the game a little fair, I'll give you 1 extra square. I'll give you a 1 by 1 square. Anybody see a way to have 2 rectangles? I mean 2 squares down and get a rectangle. Okay, how do I do it?
That's right. So you
I want to put down 2 squares and have a rectangle. How could I do it?
can have the 2 1 by 1s.
I can have the 2 1 by 1s. What can I do next?
Well, you can. It's like the Fibonacci.
It's the Fibonacci. Then I put a 2 by 2 here.
Now what?
Now what? Now what? Now what? Now what? Yeah. So this is another way of defining the Fibonacci's. We forgot to bring the fuse tree thing we did. But the Fibonacci's tile the plane, and there's a beautiful theorem here.
Can I take a more?
What?
50, wait,
After 13?
55.
No. What's after 13?
Oh yeah, 34, 55, 89, 144, 233.
We forgot 21,
Oh.
which is very important on college campuses.
34,
So I'll just end with one quick.
89,
I'll end with one quick
144,
observation.
233,
Because this is a rectangle,
77,
the area of the rectangle is the sum of the areas of the squares. Each square, its area is the square of its Fibonacci number. But this Fibonacci number is 8 by 13. The square rectangle is 8 by 13. You actually get f1 squared plus fn squared is fn plus 1. It's a geometric proof of this identity for Fibonacci. I'll let you think about that. Okay, that's a good place to stop. Please feel free to grab munchkins on the way out.